All right, now let's do the second page. So we want to compare which object has greater displacement and average velocities in these situations. So here we go. I have here object A and B, and we want to compare the displacement over 5 seconds. So let's remember displacement means final position minus initial position. And when we look at this graph, these two graphs start and end in the same place. Therefore, x final minus x initial is equals the same for both. So we'll just take note of that. Now let's look at the displacement from 2 to 5 seconds. So when we look here, we see object A winds up here at 2.5 seconds and object B winds up here. Now if you want to, you can actually mark things. Like you can say, hey, let's make this 10, for example, let's make this 5. And what we see is that at 2.5 seconds, if we were to use these numbers, so using made up numbers, using my made up numbers, okay, object A would be 5 minus 10. Object B would be like, I don't know, 8 minus 10. So if we're going to go by magnitude, what we would say is that object A has the greater displacement. Similarly, when we look to see the displacement from 2.5 to 5 seconds, we see that object A only moves this amount, whereas object B actually has a displacement that's much bigger over the second part. Sorry about that. Now, we want to compare the average velocity. There's actually a trick to this. The way you compare average velocity is you take the displacement and divide it by time. And the time's the same for each object. So what that means is it's equal here, because it was equal for the displacement. Whatever answer you get for the displacement is going to be the same for the average velocity. And so for 0 to 2.5 we compare, because again, displacement, so this is displacement. That's x final minus x initial. And average velocity is going to be displacement divided by the time. And since the time is the same for each, if I get the same displacement, I get the same average velocity. If A has a bigger displacement, then it has a bigger average velocity. Finally, we want to compare the instantaneous velocity at 5 seconds. And the way to choose that is whichever one has the bigger slope. So let's compare. Who has the bigger slope? I look here, this is a steeper slope, this is a less steep slope, and therefore, for this one, the instantaneous velocity of B is bigger than that of A. Now, moving on to number 2. We have the same situation, but now we're looking at a velocity versus time graph. So let's go ahead and compare things. I want to know how the instantaneous velocity at t equals 0 compares. Well, looks like object B is going faster. When I look at it at 2.5 seconds, object B and A are actually going at the same velocity. When I look at them at 5 seconds, object A is clearly going faster when I read it off the graph. Now let's get the displacement at 2.5 seconds for each of the objects. So for object B, this is actually a little easier. That's x equals v naught t, because it obeys the buggy lab equation because it's moving at constant velocity. So when I look at that, that's going to be 5 meters per second times this time here, which is 2.5 seconds. And that's going to end up giving me 12.5 meters. Now let's compare this for B. To get object, sorry, this is for object B right here. Now let's go ahead and look at object A, which is the one that's accelerating. When I look at object A, it's a little bit different. I need to get the initial velocity, just like we did in that quiz, which is 0. The final velocity here is 5. And we need to get the slope of this graph. When I do that, that's going to be 5 minus 0 divided by, so acceleration is going to be 5 minus 0 over 2.5 minus 0. And that's going to give me an acceleration of 2 meters per second squared. Now I can plug all of that into the equation v squared equals v naught squared plus 2 times a times x minus x naught. So when I go ahead and put in the numbers, I'm going to end up getting 5 times 5 is 25 equals 0 squared plus 2 times 2 times the displacement. So when I actually end up simplifying and getting my displacement, my displacement ends up being 6.25. What that means is from 0 to 2.5 seconds, object B moves further. Now, we can actually repeat this calculation, but now we go all the way to 5 seconds. And what we'll actually end up getting is that they end up getting an equal displacement when you do that math. And I can actually show you that up here. So object B, it's going to be V naught times T, which is going to be 5 times 10, which is 50. For object A, I still have an acceleration of 4, but I have V squared equals V naught squared plus 2 times A times X minus X naught. And this ends up being that 100 squared equals 10 squared, which is 100, equals 0 squared plus 2 times, and I'm sorry, this is not over 10 seconds for B. It's over 5 seconds, so I get a displacement of 25 meters. I apologize for that. This is 5 seconds, not 10. So 100 squared equals 0 squared plus 2 times the acceleration, which is 2, times the displacement. And I also get a displacement of 25 meters for object A, so they end up being equal. Now, again, to compare average velocity, I just take the displacement and divide it by time, so the answer should be B and equal once again. When I compare the acceleration, object B has no acceleration, whereas object A actually does have one. So object A is the correct answer for that one. So that wraps up the second page of this exam, and in the next video, we'll move on to the third page.